Hello and welcome to my Physics Lab 2211, lab number 4, Oscillations. So as a brief introduction, our purpose was to track, analyze, and model the movement of an oscillating spring mass system, and then to compare the change in energy, as well as the overall conservation of energy within the model to the real-world system. And a brief summary of our results is that the model closely matched the behavior of the real system. The change in total energy was equal to 0 throughout the experiment, and the period of oscillation was approximately 1.5 seconds in both the x and y axis. So the main ideas for this experiment is called the energy principle and the velocity and position update equation. So per the energy principle, the change in the system's total energy is the sum of the change in each type of comprising energy. For this lab, the ones that are relevant are kinetic energy, as well as spring and gravitational energy, using the equation shown to the right. And each of these comprising energies are defined by the following equations shown below. To generate the model, we use velocity and position update to iterate the state of the system over very small intervals of time. So procedures, we first tracked the motion of the provided oscillating system using tracker. We then generated a model that iterates the energies inside the system and uses changes to net force to update the velocity and position of the model over time. We then iterate changes to the system's energy using the position and velocity model. We then compare the model to the behavior of the system, and then we determine if the system's total energy changed over time. So here is the system in question. The system is the spring, the mass, and the earth. The surroundings are none. The y-hat axis is upwards vertical, and the x-hat axis is rightward horizontal. So to create the model, the first step was to declare the mass, initial position, and velocity of the block. We then declared the gravitational and spring constants, as well as the length of the spring. We then established the length and orientation of the spring at the start of the experiment, and we computed the system's initial energies. After declaring the initial energies for the next step, we calculated the spring, gravity, and from that derived the net force vector. And then using velocity and position update, we updated the position and velocity of the block. And we finally updated the spring's spatial position and length and iterated the change in each type of energy over time. So discussing our results, in estimating the oscillation periods, you can see from the gray lines that the distance between peaks, in this case the x-axis is time, so it's just time per period of oscillation, is roughly 1.5 seconds, both in the x-axis and in the y-axis direction. And is the energy principle satisfied? Yes. Note that while the gravitational, spring, and kinetic energy changes over time, the net change in energy, which is shown as orange, is equal to 0 for the entire experiment. When one energy level changes, the other two forces change by an equal amount in the opposite direction, such that it always sums up to 0. For example, over the interval of 0 to 0.5 seconds, the potential energy of gravity decreases, but the spring's potential energy increases, as does the kinetic energy of the system. So finally, discussion of error. The video provided was low resolution, and imprecision in tracking the block as it moved resulted in imperfections in the experiment's recorded motion, as it was difficult to pinpoint the exact position of the block. And the time between iterations is not instantaneous, which means that each step is an approximation of the block's position at that point in time. This will result in compounding errors if the model is allowed to run for a long enough period of time. Thank you.